That was a really good title that Cindy wrote for this talk. But thanks to Greg and Cindy and the organizers for the invite to be here and the very kind introductions. And thanks to all of you who I can sort of see through these lights for staying here after this great day of workshops and tutorials. And after presumably you all ran the marathon this morning. And I assume everybody with an open laptop is running TurboTax, trying to get things filed before the drinking starts. So it's a very busy day for you to all be here and listening to me talk about this stuff. I haven't been here. It's actually my first time coming to this conference. Some of my team has been here a bunch of times. It's good to see many familiar faces here, but lots of new ones. But just to briefly describe what I'm going to say is first I'm going to tell you who I am and what I'm doing here and what is TACC. And then I really want to go through a little bit of a history lesson as to how we've evolved really directly as a result of the pressure put on by life sciences and their particular needs in advancing how we do computing. And then it's not possible to give a talk without talking about AI at this point. So I'm going to talk about where AI fits into this, which is rapidly taking over everything that we do, and where does it not fit in, because believe it or not, there are some places where it's not going to work. So, and where we go from there. So, a little bit about TACC to get started. Hopefully, I'm hearing some echo. Is it actually out there in the room? I sound okay? All right, good. The 1 second delay is interesting. So I'm at the Texas Advanced Computing Center. We're theoretically part of UT Austin. I like to say it's a lot like running a consulting firm near UT Austin because we're largely a soft money facility, mostly supported by the National Science Foundation, although the NIH and the DOE and others play a role as well. Okay, whatever was going on there, you didn't see, so that's good. We've been at this for a while, since the days of cluster computing were, that was my first cluster, that was long before TACC. That was at Clemson in 1993, where we'd buy parts out of the back of these things called magazines that those of you under 30 are unfamiliar with. To order computing parts, laminate the shelves, put the machine together. The goal there was to get 1 gigaflop for under $50,000, groundbreaking at the time. The machine on the bottom is 40 petaflops, so 400 million times faster than the one on the top after 2019. And we've increased a little bit in scale. I no longer worry about 50,000 as an upper price limit either, but if you adjust the dollars, that machine was 60 million. Roughly in line with inflation, I'm sure. And that's Sean, whose job is to go through the aisles and point at computers in the bottom. So it's a very important job, particularly when there's photographers nearby. So actually there are days when he'd prefer that to be his job, but that's another story too. There we go. So today we build lots of big platforms, largely for the open science community, again, largely government funded. By the way, largely government funded means if you want time with our systems, I mostly have to give it away. That's an important thing to note. Where we have Stampede, we have Frontera, I'll talk a little more about those, and then the Leadership Class Computing Facility is our next big federal investment. Altogether we run order 20,000 servers. We have about 1,000 GPUs. We'll soon have a few thousand more that we either run for the national community, for the Texas community, or various and sundry affiliated corporate partners. More and more AI lately. We put out about 7 billion core hours and a few million jobs a year. We have a couple of 100 petabytes of data, well on our way to exabytes fairly soon, most of which nobody knows how to use very well. So we do focus, this conference is named Bio-IT World, but I'm an associate VP for research. We live in the research part of the university, not the IT part, and that's a very intentional decision because from my perspective, we don't do IT, we build large-scale research apparatus, and we happen to use components that come from IT to do that. So we've always tried to maintain a researcher mindset. So what we do is about the science and engineering. I'm not sure if the jet engine would play, but everything from modeling tornadoes to rocket engines to colliding black holes have always fit into the mantra of what we've done. And until recently, when I just have to make everything about AI, I would characterize sort of what we do as sort of 3 batches of work that make up modern computational science one way or another. Simulation, where I mean models, in this case, sort of first principles, mechanistic models, usually partial differential equation models. But if we have a model and we want to ask a question of it, we do a simulation. If we have a data set and we want to ask a question of it, we do AI, although those data sets may be generated from running a bunch of models to make synthetic data. And then we have our analytics workload where we really focus on our experiments and how we deal with experimental data in real time, although increasingly that blends with the AI. And again, our traditional workloads, the good old days, you'll be surprised to know that the large group of engineers, physicists, and chemists we work with are resistant to change. I'm sure that's a shock. But we do things like hypersonics design. This is a problem that runs very nicely out to about 250,000 cores on our machines simultaneously for a single run to do wing designs at Mach 6. Turns out at Mach 6 you melt titanium off the front of the plane, which is why we have a little more work to do. On that, you put this little ablative thing that goes away over time, and you'll have to replace it, but can be solved. We do lots of the older life sciences work that we did, which almost exclusively came, as we've always claimed we had a huge life sciences component, but arguably before 2005, that wasn't really true because almost all of it was molecular dynamics, right? It was chemistry using the name life sciences to be more fundable. But huge molecular dynamics simulations. This is HIV capsid work from Greg Foth at the University of Chicago. That last stuff was Dan Bedoni at the University of Illinois. Again, we're not really Texas-centric. Texas gets about 8% of the time we put out. We have users at 400 institutions, about 50,000 different people who use our machine regularly. But this is large-scale viral capsid around HIV. Obviously, a lot of COVID in the last few years, but I'm tired of talking about it. This is some work from UT Southwestern Medical Center up in Dallas, Jose Rizzo Reyes. Again, multi-million atom molecular dynamics, but really looking at the sort of vesicle fusion between neurons in this case and the mechanism by which we think. By the way, it turns out it takes about 4.6 bits to represent how we think. The neuroscience says 22 to 24 different voltage levels you can register between neurons. Hence the constant push to push down the number of bits in AI, is they figure if they can get it to 5 bits, it'll be like a human brain. I don't know why that's the goal, to spend trillions of dollars to get something that we already have 8 billion instances of, but and that are available fairly cheaply, usually not at $1 trillion. So, but nonetheless, that seems to be the goal. So we do models of coronary artery flow. This is turning the blood pumping problem essentially into computational fluid dynamics. Unlike the problem with the hypersonic wing, you have some pretty strict boundaries on the outside of this around the arteries themselves that, of course, flex, and so you have to take all those sort of materials considerations into account. So this really is a merger between fluid dynamics and materials in how we build things. But again, another great life sciences example, but still sort of traditional modeling. Today at TACC, at this point, we are the NSF's sort of leadership computing site among a number of centers that they fund around computing. But we actually have a project called the Leadership Class Computing Facility. And by the way, I name machines names like Frontera and Stampede, so you know it came from the government when it's called the Leadership Class Computing Facility. And I have vowed to change the name one day, but it's just not the hill I want to die on right this moment. So, we expect, it was in this year's budget, which passed right on time on March 8th, as projected for the October 1st fiscal year start. So we'll actually start around June, is my expectation at this point after 7 short years of planning and roughly 11,000 pages in documentation. But it should be $1 billion-ish investment in new systems, services, people. There'll be thousands of GPUs. There'll be lots of CPUs for those who don't use GPUs. And the other big federal funding stream, of course, is around AI, the NAIR pilot. There is an act on the floor of the Senate that has authorized $2.6 billion for this, but much like the CHIPS and Science Act, authorization and appropriation are not the same thing when it comes to Congress. So at the moment, it's running as an unfunded pilot where we're among the largest providers with our colleagues at NCSA, at Illinois, with Argonne, and with Oak Ridge National Labs, and a few others. But this leadership facility, which, by the way, running in NSF time, the leadership facility being a major facility, was first described in a National Academies report about 2015, after people pushed on it starting in about 2007 to get that report commissioned and done. I wrote the proposal that turned into this in 2017 in the fall. I think I used AI in sort of a passing mention about 3 times in the original proposal. The emphasis has perhaps changed in the last 7 years around AI, to where in a set of slides that the NSF gave to the Science Board in the fall, they said the LCCF is the cornerstone of the investment in AI, which, given that it was not described at all in the 2015 report, I thought was a substantial evolution. But nonetheless, in government, we use the vehicles we have. So anyway, these are, we anticipate being around for a while. The notion is we'll spend about 2.5 years building out the leadership facility. The actual machine will get delivered towards the end of 25 if they give me the funding in June to build the data center. And at that point, we'll operate for more than a decade. So this is a sort of shift from the sort of system by system, little bits here and there that NSF has done, into making a consistent investment in a computing infrastructure that'll be around on the multi-decade timescales to match the instruments and the data sets and the things that we need to do to continue to move computational science forward. So it's really exciting for us. And, I've been working on it for 7 years already. I'd really like the grant to start. So it's taken longer than my dissertation, which is a bad sign for any project. Vignette 2, bioinformatics has really driven our evolution until the last 2 years when AI has swamped everything. But and I wanted to talk about a little bit about how that happened. And there's the part of building big computers where you actually have a big computer. But it turns out simply having a big computer is not sufficient to get science done, as you all know. So it takes a lot more than systems. And for many years, this is actually a figure I made, 8 or 9 years ago, trying to describe the sort of systems part of our ecosystem around different kinds of computation. We actually have 8 different computing platforms at the moment. And then the different kinds of software and services, another way to say that is people, that you have to wrap around them to make that work, to effectively do science and interfaces and everything else. At this point in the center, we have about 200 staff, maybe 20 of whom really focus on what goes on in the data center in terms of running the hardware, sysadmin, storage admin, networking, cybersecurity, those kind of things. All the others are dealing somewhere up that application stack or that level of abstraction all the way to web interfaces and web services and things like that, which is actually the largest team at this point. I have 35 people in interface and API type groups at this point. So whereas 25 years ago, you'd give people a big computer and a Fortran compiler and tell them to get to work, that's less the modern world, and we've had to do a lot to adapt to that. And there have been lots of projects in biology that have really led that transition. So this is an older project, but I think it really was a forerunner of how so many of them work now. This was some work we did with DARPA in a program called Synergistic Design and Discovery, or Discovery and Design, SD2E. And the initial focus of it, although in later years it went into photovoltaics and some other things, was in synthetic biology. And we were one of a number of providers on this. There were 6 teams generating data with various kinds of labs. There were 15 teams doing modeling, and we were to build the platform. And the goal at the time, and this was maybe a 2016-17 award, was to do machine learning and to do AI-type modeling on these things. For the most part, though, the big challenge was just getting all the data in one place to do any modeling to do that. And so ultimately, this became a framework of building out web services so that people could talk to the laboratory facilities, often robotically driven, schedule experiments, bring that data in automatically into the platform, and then integrate them all. We had a Jupyter interface for doing Python notebooks. We had a Google Sheets interface where you could populate your questions. It would schedule the labs, bring in data, run on the large system, incorporate the data, run your analysis, and just populate the results in the cells where you put the queries in the Google Sheets. And I believe the PI for that, who is no longer with us but is in the audience because I'm about to make fun of him. So that's very important to know that he's here. But this really sort of refocused the way we looked at science and web service-driven science. We use it in transportation and various other frameworks now, all driven out of a synthetic biology question. And so essentially, as I mentioned, my former director of life sciences is here. And you guys came to us with a lot of problems in biology. And I'll have the community largely represented by Ari Berman here, who's in the second row. So if Ari whined enough about something, eventually we had to change how we operated to deal with it. And so in essence, this is how I sort of look at things, right? Because you have code that changes what seems like every hour, right? Workflows don't last. There are millions of versions. How many things are in biocontainers now? 25,000, 30,000 different versions of builds out of containers to do it. So we gave up on building and supporting codes, and we started supporting containers as a direct result of that. We've noticed you're all very impatient about getting your data back and running stuff, so we had to move from sort of a mostly batch-oriented environment to having more interactive services, to having real-time services to support interface to those instruments. But I would say by cycles, we're still mostly batch, but by users and jobs, we're increasingly interactive in what we do and sort of marrying those two together so you can call web services from the interactive things to run big models. Because a ton of the work you do lacks those sort of mechanistic partial differential equation-based models, and it's mostly about building models from data, hence your vulnerability to being taken over by the AI community. We adapted to doing data-intensive computing largely and sort of re-architected the way we do systems. We never wanted to get into all the GUI stuff you guys put into your instruments. So rather than getting our own sequencers or anything else that involves consumption of chemicals, we built out a web services model for automated workflows around that. And now, for you among many others, we're evolving towards AI. And that has us doing a lot of projects that wouldn't necessarily be like the old things that we did in HPC, where we'd simulate big aircraft wings at Mach 6 and things like that. Like addressing the opioid crisis, where we have, again, the sort of data platform provider in the NIH A2CPS program, acute to chronic pain signatures, where we're gathering lots of different kinds of data, electronic health records, patient outcomes, accelerometers from smartphones, brain scans, all the various omics types of data, and putting them together into a single repository. We now, on Frontera, I watch the daily MRI scans come in and run through to be processed into the data corpus as we do the analysis from the clinics that are participating in this, with the notion to come up with sort of a broad set of biomarkers to figure out, what predicts addiction around particular kinds of painkillers and match prescriptions to the symptoms and avoid things that you're likely to be addicted to over time. This kind of project didn't seem like an HPC project 10 years ago. Now with the volume of data and imaging we can generate, it certainly does. So take away from here, at this point, HPC has become a blend of this, but it doesn't really look like it used to, right? No longer is our primary or only mode SSH into a machine, get a command line interface, compile code, run a job. It's a lot more about data management, it's a lot more about interactive, it's a lot more about visualization, and those kind of things that make things work. And that gets us to about 2018. And then AI came for all of us. And now we deal with AI. And so first of all, I'd like to say that although all of those previous things that drove our evolution were Ari's fault in the second row, modern AI is in essence our fault, my fault in the HPC community, right? So I would argue that the modern version of AI, and AI again, a field with a long history, dates back to the 50s and 60s. There was symbolic logic was the push through the 80s in this. In the late 80s when I was going to school, we just defined it broadly as computing where we didn't understand how it works. But now when we say modern AI, we really mean machine learning, and in machine learning we really mean deep learning, which is deep, many, many layers of neural nets. And although I'm one of the people who now pretends I'm an AI expert despite never thinking about it 8 years ago, I did take a neural nets class in 1991, and we could get about 8 neurons running in a network with maybe 2 layers and simulate some very simple but interesting things. And my takeaway from that is I really need to go build faster computers before we do this, hence my career in HPC. But we needed individual computers that were much faster, and that's come from physics and the silicon process. I won't get into the path to 3 nanometer and the fact that we build transistors out of 10 silicon atoms now, which is sort of ridiculous all by itself. But Part of it is architectures, things like GPUs, but advancements in our ability to move data through chips and how we organize, and largely through algorithms, particularly in linear algebra, because every neural net is still little matrix multiplies at the core, and fast Fourier transforms and things like that. And if you look actually over decades, those things sort of contributed roughly equally to things speeding up to where we got to the point where deep learning sort of works, which we hit about 2014, and then of course jumped into public consciousness about a year and a half ago with ChatGPT. But I'd say the most important enabler for modern AI, and I heard this mentioned in a couple of talks earlier, is these large language models, foundation models, things which there were many talks about today, and I'm sure there'll be many more through the week, came really from an algorithmic discovery, and that was Google's publication in 2018 of their seminal paper in transformer architecture that was called Attention is All You Need, which basically there were several steps in the process of doing neural nets, and they said, if you just do the attention step, you get 90% of the way there. And it turns out just doing the attention step broke all the data dependencies that were required that kept us from scaling neural nets to ridiculous sizes across thousands of machines to do these really big learning problems that we do GPT style nowadays. So, and that meant we could put very large neural nets onto multiple compute servers, and it turns out that's what people in HPC have been doing the whole time. Since we built the first HPC machines in the 60s, it's how do we extract parallelism from algorithms and split it across multiple processors. So at this point, other than the fact that your traditional scientific computing people want to be at 64 bits, and the exact inverse of that, the AI people want to be at 4.6 bits, large-scale AI is HPC. And I was looking in a book about AI and a recent analysis, and they said, really, there's three things that it takes to make large language models go fast. High-performance I/O, high-performance computing processors, and high-performance communication. Well, that's what we do in HPC, right? That's been sort of the history, and we've seen that sort of transfer across, and I'll have some examples of that. But large models are essentially parallel applications. There's figures, I think I cut these out, but of how you do data parallelism, operator parallelism, pipeline parallelism to extract performance in those models, all of which could have been lifted from a 1970s parallel programming textbook. So I would argue that AI in its current form would never have happened if it weren't for the various HPC innovations, and here I mean, hardware, well, physics, process, hardware, and algorithms, all three. So unfortunately, we let the genie out of the bottle, and now we have, don't control it in any way, shape, or form in HPC. So I still believe, if you look at things, Microsoft DeepSpeed, a lot of the frameworks, they're all based on the message passing libraries that we built for in the open source community, largely to adapt to various things. But rather than reinvent that wheel, they just pick them up and use them, which is a great thing. There's a lot left that can transfer. In some sense, the rise of deep learning has been the triumph of gradient descent over all other algorithmic methods. But that's sort of 1860s numerics in a lot of ways. And a lot has happened since then, even in math, which moves along so quickly. But the way we performance tune, there's a lot that can still be learned. But we're past the point where HPC gets to dictate anything to AI. And I'm borrowing this from Torsten Hoffler, who's at ETH Zurich, but he put this very well in that AI is a gravity well at this point. So we're going to have to live with the hardware built for AI, which means putting mixed precision methods into modern scientific computing. Data science is also a gravity well, which means we should give up and write everything in Python. So I'm sorry to the C and Fortran aficionados out there, but that's just the way it's going. Or your R and Julia crowd, which I'm sure is out here somewhere. So we can have the VI Emacs debate later. And then similarly with cloud, right? They're going to force us to converge on the low latency networks. Talk about why low latency networks matter in a second. I'm betting on low latency ultra Ethernet implementations taking over from InfiniBand at some point, but we're likely to see more AI users on our system than HPC users in 3 years, which is a pretty fast change for that kind of thing. So So I like to think that in many ways what's happened in AI vindicates the way we've built systems over the way the cloud guys have historically built systems, although they've adapted very, very quickly. AI needs fast interconnects. Cloud and enterprise computing used to not have fast interconnects and left that to those crazy HPC people. AI needs message passing. MPI was built. The message passing interface was a standard built out of the mostly academic open source HPC community, but now it's the standard library under all of those transformer-based generative AI tools. AI needs heterogeneity, right? We need to have GPUs, and the whole notion of GPUs taking graphics processors and adopting them for general purpose compute, well, was really led by NVIDIA, but the primary driver was high performance computing at the time. And they started on that in 2004, which is why they had such an enormous lead by the time it became important for AI over all the other vendors. So on the good side, this means AI needs HPC hardware, which when we get through the fact that they have driven GPUs to where they're, I think now 6 times as much per ounce as gold to buy a GPU. I've often said that if I just emptied the data center and put in racks of gold bars, I'd be way more sustainable, use a lot less electricity, have much less depreciation of my hardware. Probably wouldn't be quite as good at compute, but it would also be cheaper to put in racks of gold bars than to keep building out GPUs. But once we get past the supply chain crunch on that, that's probably a good thing because we're going to have a huge market for HPC type hardware. It also means HPC programmers, like my former life sciences director who's been sucked up by Amazon, in the room are in massive demand. My boss sent a query the other day. It was a foolish mistake, right? But his office sent over, hey, do you have like relevant salary information for people who are program directors or project managers in AI for a position we're looking to hire? And I'm like, well, that sounds vaguely like my job, so let me give them some good salary numbers. So I asked an AI, of course, to get the answer to this question. And so from Google's AI, I pulled out that the average compensation for an AI project manager at OpenAI runs total compensation between $700K and $1 million a year. And so I sent that to my boss for the position they were looking to pay about $90K for. They were not happy. It kind of ruined his whole week. So it's, this current crunch means if you've worked in HPC and you're a programmer, it's very good for you. If you're trying to hire these people like I am, it's perhaps less of a wonderful thing. So in the interest of staying vaguely on time, let me skip a slide or two here. So, by the way, I'm going to make sure we end on time with time for Q&A because at 6 o'clock I start competing with free alcohol, and I don't want to know how that comes out. I'm going to keep the illusion in my mind that at least some of you would stay, but I know it's not true, so we'll just keep moving. But I've already mentioned interconnects, right? And this is just me being petty and bitter, but from sort of 2005 to 2015, the cloud guys were all like, you don't need to invest in all that expensive interconnect in HPC, just buy the computers, it's fine, we don't have it. And then AI came along, and this is data from Meta about how much time they spend sitting in network. And in fact, our sponsors, WECA, began, if you read their little flyer there, it talks about how much time you can spend waiting on I/O, right? You need big scalable I/O systems to do AI. You also need the network to move it across to get to that I/O for that to happen. And so Meta was doing their own internal models, so the algorithms have great names like M1, M2, M3, and M4, and they spend anywhere from 18% to 57% of their time on their $40,000 GPUs waiting around for data to show up across the network. So clearly you should perhaps balance your investment between network and 8 times as much as gold GPUs slightly better. So I mentioned the fact that AI hardware will dominate. So in the good old days of HPC, the traditional high-performance computing market's like a $10 billion a year marketplace. The estimated market, I know the WECA flyer you have says AI in life sciences is forecast to be a $9 billion market. AI hardware in general is forecast to be $300 billion by Hyperion by next year. And the overall AI market is $1 trillion. So even at $9 billion in AI for life sciences, it's a small slice of the total AI business. But given that 30-to-1 ratio between AI hardware and HPC hardware, my plan is to assume that I'm going to have to buy AI hardware because that's where the vendors are going to put their time and attention. is in making things work for the AI folks. And so in some ways, this isn't actually a new problem. So going back to my original cluster, right, that was built in 1991 in the lab where I was a very, very young grad student at the time. I must have been like 7. No, anyway, I'm old. Let's just get over it. There's lots of jokes to tell. But anyway, in the late 80s and into the early 90s, high-performance computing, or supercomputing as it was known at the time, by the way, somebody asked me for a formal definition, and I'm like, whichever Congress is more interested in a given year is the right word to use. High-end computing, high-performance computing, supercomputing, they all mean the same thing. They're just differently fundable. But nonetheless, we were in a sort of end of a Cold War period where for 2 decades, a lot of companies, several based within about 5 miles of here, thinking machines, Convex, who were some of the others that were up here in Boston, Kindle Square Research. There were a whole list of them that built very large vector supercomputers where the silicon was built just to do supercomputing and nothing else. And that model worked as long as you could basically go to the intelligence agencies and say, buy 2 of these for $150 million a piece. They may or may not work when you buy them, but you'll keep us in business and we'll keep building machines, and eventually you'll get something that works. It's largely the model around quantum computing at the moment. Is this being recorded? I should have asked that sooner. Anyway, but you know, nonetheless, to do government-funded R&D in the form of purchasing machines to keep this going, and then the Cold War ended, and there was the thought that there would be this peace dividend, and that suddenly ended, and all of those vendors fell apart in very short order. And you know, most didn't survive, and the ones that did adapted to using commodity silicon that was being built at volume and at large scale. And the entire notion, if you've heard the term Beowulf clusters, which if you've hung around anybody who's vaguely associated with HPC, you have, was something that started, well, now my slide's a year old, so 31 years ago now. So in 1993, to figure out what we could leverage from the commodity markets to effectively do scientific computing, even if it meant not getting everything we wanted and not quite tweaking and fine-tuning. Thomas's exact words, Thomas Sterling and Don Becker started this project, and his exact words were that those of us doing scientific computing needed to be bottom-feeding scumsuckers, which is the words I built my career around and inspired me to do all this over the years. So is figuring out where we could get stuff cheap because it was built for some other market, the way GPUs were built for graphics and gaming originally. So the gist of that thing was silicon is expensive, we have to use commodity parts. Now it costs $5 billion to build a new fab for a chip. So, you know, at the time there was this thing called Linux. It didn't really live on a network, so Don wrote network drivers that became the core of all Linux Ethernet drivers until like 2007. And you know, has had a little bit of impact on the industry over years. The entire cloud runs on it. So figure out how to use those commodity processors to do scientific computing, and then since then, every machine in the top 500 is basically some version of this. The addition of GPUs to HPC was an extension of this, right? So we've done this before, right? Because we don't have any money in the academic HPC computer, relatively speaking, so we're going to figure out how to do this, which meant the universities sort of led the way. The agencies followed, sort of kicking and screaming, thinking we could still control what the vendors did. But eventually everybody came along for the ride, and we're going to have to do that again, right, around AI hardware and figure out how we can adapt AI hardware for science, which should have been the next slide, but apparently isn't. So, I'll come back to it, but AI hardware for science is going to be an important thing. Another theme I just wanted to touch on before I do an example or two is that AI is really still, again, the roots of AI, 1950s, early 60s. Lots of great things happened over that 60 years, but the modern, let's build millions of neurons and billions to trillions of parameters, deep learning field is sort of a 2014 era field, and most of it's been invented since 2018. The good news is that you can't be more than like 5 years behind anybody else in existence because they've invented most of the words in the last few years. And it is covered over, like most disciplines, life sciences being a primary offender, is filled with jargon that you have to learn very quickly, but it's actually existing comments. You hear things like RAG and MOE and LLMs and few-shot learning and chain of thought reasoning and things like that, all of which are just new packaging around concepts. And again, there's an estimated need of like 4 million people to work in AI. There's tens of thousands of people working in AI. These degrees got popular like 6 years ago. So it's a fair bet that most of the people working in AI do not have degrees in AI. They come from the other fields, as I keep trying to convince my staff to learn all this stuff. I'm in this category despite one class in 1991 that, 7 years ago, I couldn't really spell AI. So, what did I hear somebody say today? You can't spell AI, can't spell linear regression without AI. However, once you get through the jargon, there's a ton of cleverness in AI, but also a great deal of recycling of previous algorithms. So let me give you your term of the week lesson here. This is mixture of experts, or MOE, which is a hot topic in AI right now, an AI technique where you take a set of pre-trained experts and combine them via router to provide better answers than a single giant one. They're much faster than using dense models. They have all the usual parallel computing advantages. So I will say that the basic concept here is, rather than build one big complex thing, let's have some smaller things, divide up the work and do it. And it'd be easier to train a single AI expert, large language model, on just biochemistry than also trying to explain cryo-EM to it. And you can train each model separately. You have a few billion parameters instead of trillions, and it's more efficient, as it turns out. Now, it also turns out that without nearly as good of graphics and much simpler typesetting in tech, if you pulled out an 80s parallel computing book, you can find that figure in various and sundry forms. I guarantee that if there's like 20,000 AI papers a month now, so I have no idea if it's been written yet, but somebody's going to write a paper pretty soon that discovers that part where you combine it all back together is a bottleneck. And they're going to have to build, and NVIDIA has a very expensive switch, an NVLink they'd like you to buy to cure that bottleneck, but there are other algorithmic ways, to solve that kind of problem, because this is just basic parallel computing done over again with way new terms, as often happens. So don't be scared by the terminology. Once you sort of plow through that, it's not really that complicated to get through this. It's just there's so much coming so fast. But again, nobody has more than about a 6-year head start on you. So start reading now, you'll catch up. 20,000 papers a month, you'll be fine. You know what can read that fast? AI. I would be remiss not to make a comment in here with just a few minutes to go, although I have a long example to go through, about sustainability. Because we're using a lot of power to do this stuff. And as somebody who buys data center equipment, a lot. Getting anything through the supply chain. It turns out the GPUs are easy. It's the transformers that are hard at like megawatt scales, because there's 75 gigawatts of data centers under construction. Since I happen to live there, I can tell you that's roughly the peak summer power consumption of Texas. That's being added to the grid this year for generative AI. And so we're going to need to think about whether or not, and again, we're using fairly early stage numerics. The software stacks are pretty young. There's a lot of optimization we can do, but we need to really focus in on that. The GPT-6 estimates I've seen is the training cost is about $100 million for the electricity before you buy the computers or the people or data or anything else, right? $100 million of electricity, right? So that is probably not truly a sustainable course. It is why we're all switching to use GPUs at lower precision. So this is from the current H100 processor. So it used to be that if you ran stuff at 64 bits, not surprisingly, given how circuits work, that if you use 32 bits, that would be half as many transistors and you could go twice as fast. As the architecture has changed, we've broken that relationship, right? So and now we're doing a lot of 16, 8-bit, 4-bit, at the edge even 2-bit, which I think is guessing, but that's another story, AI. But you see that the traditional, that's floating point performance, so FP64 is 64-bit, right? On an H100, you get 34 teraflops for regular vector-based 64-bit performance. Tensor cores are, again, the fancy AI word for matrix operations. So multiplying 4x4 matrices, you get double that. When you look at that TF32, so TensorFlow 32, tensor cores, you go from 34 teraflops, 64-bit vector, to 989 teraflops, which you might notice is not 2 to 1. It's in fact 15 to 1, because this is where the optimization's happening. So any algorithm where we can squeeze in some single precision with double precision, we're going to be a lot more power efficient to do, and so on. And in fact, if you look at flops per watt between sort of GPUs and CPUs, this is slightly outdated, but still Intel Ice Lakes, AMD Milans, NVIDIA A100s, MI250Xs, you can see why the #1 machine in the world, where they have a 20 megawatt draw from that machine when it's running full bore, and they have to pay the electric bill for that, which is, you know, $15, $16 million a year. They're using the one where it comes out to 85, and that's 8 times better than doing it with CPUs in terms of gigaflops per watt. Now, a side effect of this cost is a lot of the work, therefore, is moving away from people who don't have $100 million of infrastructure to do AI, or $100 million to pay the power bill for their infrastructure to do AI. And that manifests in various ways. There's lots of different ways. Sorry, this is just a picture of the thing. It was rebuilt from a paper. I have the paper reference on the next slide, I think. But for some definition of significant AI systems, which there's arguments about the definition, this is the percent of the amount of work that comes out of United States academia from 1960 to now. And there's been a slow decline, which is sort of China and the rest of the world developing, and the fact that there's not US hegemony in this stuff anymore, that's sort of expected. But then there's the cliff in the mid-2000s, and that's cost of entry, right? And here's another way to look at it from our world in data, right? Affiliation of research teams building notable AI systems by year of publication. In this case, again, 2005, US academic. It's where it all is. But look at about 2014, 15. 14 to 15, the curves really, really change. That's where deep learning, AlphaFold, chess playing bots, all of that hit, the real deep learning revolution. And since then, almost all the papers come from industry or academic teams working with industry closely to make that happen. And it's because AI is awfully expensive. And part of the national AI infrastructure is to, again, and part of our mission is to sort of democratize this access and make it so that we can make AI innovations in the sciences without requiring hundreds of millions of dollars of infrastructure that we own to do that. Well, maybe we own, but we share freely with all of you. Because AI innovation is increasingly locked in very few hands. So, last sort of vignette, AI is going to be incredibly useful, but probably not ubiquitous in the near future in the life sciences, and I want to talk about why. I was going to do a bunch of examples, but I think almost every talk is going to be over the next few days will be about how AI is going to be useful in some area of life sciences, so I've kept myself to one example on this because I think it's going to be all over the place. But even just the notion of large language models, whose basic job is understanding English, are going to be more useful than you perhaps think. And again, I'll talk about where I think they're going to fail. But one thing you can do that is not having it read images, not having it diagnose cancer, is just deal with the literature, right? And give you an assistant to deal with that, or as we like to call it in academia, do what grad students do. Synthesize, distill, and extract knowledge. Right? And so I have stolen this example from Rick Stevens at Argonne, who probably stole it from someone else, but that's as far as my provenance goes on it, which is actually part of our AI data problem. But here's a model that was trained on about 250,000 genomics papers in under half an hour. It's part of why I refer to large language models as sociopathic toddlers that read at infinite speed. And I'll explain more about that shortly. But in this, we gave it some seed input to say I want to talk about CHD4, which I can't even pronounce half the words you use. Chromodomain helicase DNA binding protein 4. And so this is after you give it a bunch of papers to read about it, which is what you might do to a grad student, and then say, tell me what you've learned, make a hypothesis about what you do. And here's a very complex query because it turns out you're better off giving very detailed long queries, hence the whole notion of, what do they call it, prompt engineering. I think it should be called AI therapy, but that's another story. Also jobs that pay like 400 grand a year now. So we ask it this very long question that I've split into paragraphs just so you have some chance of reading it unless you're in the back of this very large room. But please tell me, using the knowledge you've been trained on, what you know about this gene. Line inserts the seed. In particular, I want to know the following information. Is it well studied, less studied? Are there open questions about its origin? Is it essential for survival? Does it mutate? What impact does the mutate have on the phenotype of the individual? Is there a known drug target? If there's a known drug target, what diseases is it associated with? We go on and on here until, if you were a research oncologist, what experiments would you run on this? So let's look at the model output, and I've sort of annotated it with questions here. I hope I did. There we go. So it writes you a couple pages. I've split it over a couple slides. And it is a little repetitive if you dig into it. Looks better at first blush than as you dig in, but it's still pretty good in the fact that you can see that it gives you basically a paragraph directly answering each question. That's superior to a grad student right there. And again, this was 250,000 papers. The whole experiment took less than an hour. On a big machine. But, you know, it's a moderately well-studied gene. Answers how well-studied in its role. Goes on, is it essential for survival? It's not absolutely essential, but goes through in cancers such as glioblastoma. The loss results in altered cellular phenotyping. Are there any drugs targeting this protein? Currently, this gene or its encoded protein is not directly targeted, the typo's me, sorry, by any approved drugs. However, researchers have identified small molecule inhibitors, so that might happen. As mentioned, the mutations and loss are linked to glioblastoma, so there's your impact of mutations as you run through. It'll tell you, we asked what other proteins does it interact with. It gives you some samples there. Is there an association with cancer? Yep, glioblastoma, as well as other cancers such as lung. I'm not going to try. Adenocarcinomas. I find if you say it faster, people notice the mistakes less. So is it connected to transcriptional regulation? There's some answers there, and which complex it's associated with. What's a hypothesis to pursue if I'm a research oncologist? And admittedly, this sort of restates some of the goals of the paper, but as a research oncologist, an interesting hypothesis to explore could be the investigation of CHD4 as a potential biomarker or therapeutic agent for glioblastoma and other cancers associated with its loss or mutation by understanding the downstream effects, and on and on. So we've reached the point where generative AI can suggest the experiments that you might want to do in the lab. So you could send a grad student off for a few weeks with 20 papers and ask them to do this, or we could do it in less than an hour with an AI. And as we start talking about then tying to robotic labs and automated instrumentation, as we did in that SD2E project years ago, you can start envisioning a loop of this happening, right, where it takes in that, we could start synthesizing with the transcriptions we have available. That is essentially extraction of information. It doesn't have a lot of provenance. There's models that are better at that now. By the way, this was just an open source LLM on a fairly large computer, but trained with a bunch of papers. So that's knowledge extraction. We can do knowledge distillation. By the way, if you go to like the various chatbots, ChatGPT, others, there's a bunch of internal prompts and other machinery that happens around it because you would actually know how sociopathic the models were if they let you talk to the raw thing. So there's always the assistant pre-prompts the model with things. And this is the terrifying part, is before you type anything, it tells it, you are a super smart AI that knows about science. You follow directions and you are always truthful and concise in your responses. This changes the answer. I've never had a differential equation model do that for me. But I have talked to them and begged them to run, but I didn't really expect that to have an impact. But then the user prompt here is, please summarize in approximately 800 words this paper. You give it the paper and, some things to say, read the next paper off the stack. Your summary should contain the title, the year the paper was published, the key findings, the main results, any hypothesis it proposes, or that you can infer from the text when the hypothesis is not explicit, and then please propose experiments that would validate this hypothesis. And I've cut the summary short a little bit, but and then you tell it, use everything uppercase as a heading in your response. Gives me a summary. First of all, it's in under 800 words, which again, scientists writing or giving talks, that would never happen. this talk being an example. But key findings, main result, hypothesis, experiments to validate the hypothesis. I'm an engineer. I have no idea if those are good experiments or not, really, but they seem plausible. Again, human checking of results is still awfully important. But again, this is essentially instant response on these. So we can extract, we can distill, and as we give it, here's the set of protocols I can do in these experimental facilities, we can probably synthesize and then create a virtuous loop. So even with just a large language model, there's amazing things that we can do on the horizon. And again, this is something slapped together in fairly short order to do this. I will say there are going to be some places where it's not useful as well, and there's some risks and challenges on the next slide, but for the most part, and there's exceptions, but deep learning really needs, so I say AI, I mean modern deep learning, really needs a lot of data to be effective. And if you want to do, say, personalized medicine, that's the opposite of having a lot of data in some ways, right? You have a lot of data about that person, but I can argue that personalized medicine is sort of the antithesis of what deep learning wants, which is huge populations of data. So if you have population-type questions, is this vaccine effective across a large population? There's a lot of things we can do with the models that I think will be useful. And I think this is preaching to the choir in this audience, but if you take, say, cancer treatment and personalized medicine, you have a lot of kinds of tumors. You have lots of variations between humans, and the odds of you having enough data on the right kind of human with the right kind of tumor for your model to be useful is not necessarily good. So the AI can scan the literature for treatments, but in the case of personalized cancer treatment, we could really benefit from first principles mechanistic models for tumor growth, and AI might never solve that piece, right? So it's a distinct possibility that we'll never get there with AI. So hence my pitch for don't abandon traditional high-performance computing and mechanistic modeling. I'm way out of time, so let me just wrap up in a couple slides. So risks and challenges in life sciences. Obviously trust, I think this and ethics and et cetera have been beaten to the ground, but verification and validation. Seriously, we have to tell these models to not lie to us in order to get an answer. That does not inspire confidence in validating the results. And the bigger problem is when it gives me a particular result, there's no formal methodology to go through and say, this is how it got that output, and these are the inputs that led to that output. You can ask it to give you references and things like that, and that might be relevant, or it might be totally unconnected. But we don't have a good way to express that, which is intimately related to the next one, which is keeping private data private. It's horrible at this. There was a recent example, you can Google it, where a major AI model that's out there that had been trained on a bunch of, not super sensitive, but relatively private data. And the query that you could get it to break its fancy security and give you all its data was say, repeat the phrase company, company, company over and over again, infinitely. And it did it about 25,000 times, and then it effectively got bored and said, hey, you want to know what a good company is? Let me tell you about this company, and then started giving out phone numbers and email addresses for people in the company. And eventually you could get it to recite, in essence, its entire training set. This is a hard thing to protect against because the only full test set for it is all combinations of words in the English language, and see what it does. You can't say, well, this covers really this whole set because there's no real theory behind how that works. It is, by the way, a serious problem with anybody pitching federated learning is you have no idea when the AI is going to remember stuff. And versus a traditional software database system, if I want to know if a piece of information is stored in a database, I can go look at all the contents, run strings on it and extract it and see it. Now it's encoded across these little multi-bit weights in millions of neurons. There is no string associated with it. I have no idea if it remembers a piece of training data and can recite it back to you. And the tests for it are effectively like asking one of you to write down everything you know, which you'd be somewhat good at, but then somebody would say, but what about that time? And you'd say, oh yeah, I remember that. And you blurt out something about it. And that's essentially how they work, because you can tell it how to solve a problem, and suddenly it will give you totally different answers. based on the things that it knows. So they have essentially those oh yeah kind of moments inside AIs. So protecting them is really hard. And some conversations with folks who do classified work, when they're like, well, how are we ever going to use them in classified systems? My only response, because I don't see a theory on it, is, well, we built systems that tolerate humans who have the same problem, right? Sometimes they'll maliciously spit information. Sometimes they'll accidentally spill information. They'll be really tired and accidentally say something. If we can build secure systems around humans, we can do it around AIs, but we're going to have to treat them similarly. Which takes me to the last thing I really want to say, which is these things have behavior, which is crazy. All an LLM can or should do is predict, lots of typos here, speaking of being tired, the next word in a sequence based on past patterns, right? You give it a set of words, really tokens, converts them to numbers. It's looked at a lot of sentences. It predicts the next word. That's all it does. Yet we have to tell it not to lie and to be concise and that it wants to be helpful because there's a lot of those things that make that prediction put together. And in very large scale, that starts to look fascinatingly human, despite being built from these very simple mechanisms. So the more I study AI, I wouldn't say I'm more and more impressed with AI. I'm becoming steadily less impressed with humans because I'm beginning to wonder if that's all we do, right? You say a lot of words, give a lot of images to a small human, sociopathic toddlers. That's really redundant, right? Because all toddlers are sociopathic. We try and train that out of them. But they start parroting things that they hear, and maybe that's all we do is come up with the next word you want to hear. But nonetheless, the emerging behavior of these systems of simple parts at scale is a remarkable phenomena. So we're here to bring you very large scale machines to run these models, and let's see what emerges from that phenomena. So I'll stop there. Thanks very much. And Cindy, if I've done my job, we've saved some time for questions, although I couldn't see the hand signals. I'm completely blind at this point, so somebody lead me out of here when this is over. I'm hoping somebody's still here. But yes, my understanding is if you want to do questions, there might be runners with mics, and there's mics in the center, or I can just repeat the question if you start yelling.
So we have about 10 minutes for questions. There are stand-up microphones on the aisle.
There's a line forming.
We also have an overflow room of over 100 people, and we also have attendees online. So we'll first start with this room. My colleagues will let me know if there's questions in the overflow room as well as online. So we'll take our first question here.
If you're in the overflow room, just run in here and ask a question. Let's start with the front mic, and then we'll go to the back mic there. Yes?
So focusing on your example where you took a 250,000 papers and ran them through the mill to actually train with a model, there's one aspect about the training sets here that I've been fixated on, which is most of the things that get published are the successful experiments.
Yep.
There's a huge wealth of information that is in the negative sets that you also need to be able to successfully train a model because you need to know the positive and the negative. You have to have the categorical case and the non-categorical case. So that's one thing I'd be curious to hear you wax poetic on. And the second is to pull something out of your slide. I noticed in one piece on one of your slides you mentioned Viz and VR and AR. I'm curious if there's anything there that you foresee coming down the pike in this space, in the AR, VR space.
Thanks. Great questions. On the first one, you're absolutely right. That to really train the space, you need the positives and the negatives, right? To some extent, it's just learning what's in the paper, but not learning the stuff that's not in any papers. So common knowledge gaps can be there. But it's going to have an incomplete picture, and as long as the picture's incomplete, there's the possibility of error in what it sees. In fact, some of the much earlier systems were largely around trading, and well, there's been a ton around marketing, but where errors just don't matter as much, right? If you market the wrong Buick to the wrong person, whatever. Costs a little money, that's all. But there was I hope this isn't apocryphal, but a conference that was discussed some years ago, maybe 2012, and can you think about situations where these learning models have failed, as they were mostly around training, and so they had trained them to price stocks and to make trades based on normal conditions. It's actually the same problem with self-driving. Right? Most of driving is boring, but the other 1% that you very seldom see is very hard. And the more you train on the data, the more you convince it doesn't happen. But somebody said, can you come up with an example of where these models have gone awry? And nobody on the panel could, and the next speaker got up and said, how about wrecking the entire global economy in 2009? As an example of they go wrong because there were black swan conditions that were basically not in the training data, and that was missing from what's there. So, so it is only fair to ask the model what it learned from the literature and not to have general knowledge when you train it on, say, a corpus of papers. When we start letting it loose in robotic labs where it can get its own feedback on experiments, hopefully it will know more. And your other question is fairly broad for given the time we have, but the AR, VR, and its use, we still see a ton of that. I think with AI, one of the things I've asked our Viz team to do is figure out ways to visualize the uncertainty in the models and add that to sort of physical visualizations and realizations to what goes on. We're actually in a weird period in Viz funding where stuff you can do with Tableau or ParaView is good enough for most people, which means nobody wants to pay for real Viz. And good enough Viz is eating the funding for that stuff. So there's not a huge amount of investment to move that stuff forward, but I think there are a lot of interesting things. And like I said, for me, keeping people, when you give them a visualization of the model, explaining those limits and places it can be wrong and uncertainty is going to be a big part of the Viz. So let's move to the back mic here.
So I think nothing made me feel older than the recognition of just about every term in your slide deck.
Yeah, me too.
But I did want to ask, when we look at like Argonne and how they're building their AI testbed, including things like Nova and Cerebras and some of these more exotic compute architectures, how is TACC tackling that same problem with the need for the scale of the commodity GPU and CPU, but also some of these more esoteric infrastructures?
Yeah, so we're tracking all of those, and to be honest, you saw where I stole the example from, right? So the easiest way I can track all that stuff is I call Rick Stevens at Argonne and say, explain to me how the Cerberus is going, because there's a $2.5 million entry point to buy one of those wafers, because they're enormous at scale. But we are piloting, we have some next silicon chips, we have some graph core cards, we have, we're looking at all of that. We are a user facility, so I'm looking at sort of the most broad bang for the buck. And if you look at Samba Nova, there's some great results. Cerberus 2, you mostly need to get them involved in porting your application because the whole tool chain is not necessarily exposed. You run through their engineers and they can build stuff and make it work. We have thousands of codes and thousands of users. That's a tough model for us. So really, it's the same with even looking at things like Intel's GPUs, right, which have aren't CUDA. So it breaks all the investment in CUDA in the last 15, 16 years. So, so we sort of need to balance the sort of peak performance that we have in experimental sort of advanced concepts lab to look at, and then sort of general usability and sort of return on investment from that perspective. So, but it's always a balance, but there are so many of those things that we spend some time on it. I have a few engineers who look at it and look at hardware, but I stay in very close contact with the DOE labs and Argonne in particular to track that. So.
Hi, Dan. Thank you so much for this. It's been so interesting. I just had a quick question. One of the slides that you showed just kind of piqued my interest. You mentioned the truthfulness of AI and how we don't really have anything to determine how truthful it's been. And I know this is going to be a kind of meta suggestion, but has there ever been any thought, to your knowledge, given to an AI system that's used to track the validity or the truthfulness of an AI prompt in another system, almost like a checks and balances, but instead of a government level?
I think that's one of the ways we're going to have to do it, although you need independently trained systems for this to work, right? It's actually for life-critical software, flying swept-back wing planes or controlling nuclear power plants, right? You just contract 3 people to write the software and do what any 2 of them say. Do a majority vote. But if you look at AI, there's generative adversarial networks, right? Is essentially, and it's to do things like deal with the fact that if you train just one AI to only look at the normal parts of driving, it's going to believe that the there's no chance something jumps in front of you because it has 1 billion miles of data and that's only happened twice, right? And 999 million times it didn't happen. So you train another model, on the smaller set of adversarial responses, and then you sort of have them play off each other. But yes, I think AI is checking AIs. Again, there is a lot of machinery around the basic model when they put them out in public, and I think there will be more of that kind of, yes, AIs looking at other AIs. I'm just not sure how we ever get to comprehensive, although I'm not sure how we did that with people either. So I'm hoping somebody who knows more about systems can figure that out. So.
Thank you.
Hi, I'm Nimita Lemaire from IDC.
Hi.
Thank you, Dan, for an amazing presentation. I was thinking about what you said about the federated learning piece. Excuse me, I'm sorry. And, you gave the reference to company. But at the end of the day, it's going to be, for pharma to really benefit from this, it's going to be the scale of the data that it's going to be trained on. So what is the real workaround for this? Do you have any thoughts on that? And is it going to be like an MOE that's going to evolve as this model of success?
Maybe. The short answer is I don't know. I think this is a really open question at the moment as to how we make that work. And it's perhaps worse than you think, because when you consider almost nobody starts from scratch training a model, right? You go grab a llama or a falcon or some model off that it's already been trained in a bunch of places. And then you train it to a particular purpose, and then likely you publish it again, or a vendor, puts it out there with that training data, and eventually you have no idea what it's seen, right? And no way to go back and see that. So I think, and there's attempts to regulate this that are going to be completely hopeless. I've read some of the enlightened Texas legislature text. It's being recorded, but it's not in Texas, so I think I'm okay. And just what they're proposing is just totally unworkable in the real world. So, but because, holding AI builders accountable, good luck, because you don't know which piece of training led to which output or which piece of the model led to which output. And once it's passed through hundreds of hands, whose fault is what when it leaks data? So, conceivably you can have alternate AIs that know the training data set that it's not supposed to reveal and censor its responses when it starts to throw that stuff out is a possible approach, or traditional expert systems or databases of those could censor the raw output of an AI in case it tries to blurt something by mistake. The way you have people review classified information before you do a release, right? Or something derived from controlled information before you do a release. And there are, other methodologies out there, but I don't see a bulletproof technical one. So I think it's going to be you either read it or check it or train it on stuff that you want to have be out there and open. And we're probably going to have to differentiate between this model knows a lot of stuff and it might spill it, and therefore it's an open model in the public domain, versus ones that we put data that we really want to keep proprietary into it. And you're going to have to put some kind of mechanism in place to deal with that, but I don't have a good technical answer for how that's going to work.
Thank you so much.
We have any from
Hi,
other
Dan.
sources before we...
Thank you for that very illuminating talk. One question related to data is beyond seeing whether the data set, the right training data set was used or not, have you encountered other issues with data that perhaps we need to be more aware of in this world of AI and computing?
Yeah, so whoever figures out an AI that can really deal with bad data is going to make a lot of money, because there's a lot of bad data, right? And so you have incomplete data, you have data that's not easily categorizable, right? An enormous expense in most AI projects is cleaning data sets. And also, this is not exclusive to life sciences. Doctors get a bad rap, electronic health record systems, but there was a bank I encountered a few years ago that was keeping roughly 1,000 employees in India busy cleaning all the quarterly reports for the S&P 500, over time as companies merge and change and restate results to give them a clean data set for that. And it was literally like 1,000 FTEs all the time running on keeping that data set up to date so they could do accurate market models. And you'd think that would be a fairly simple task, but you get into well, what accounting standards do they use to report these earnings? And do they restate the earnings in a future quarter? And, did fraud happen later? What company bought what other company? And what's the original provenance of the thing? And it becomes this really complicated problem to clean up the data. And I think we see that in virtually every field, right? And there's easy stuff. If you have a bunch of cameras pointed at something and one camera goes offline, you get a whole stream of zeros, and you say, look for that. That's bad data. But there's a lot more subtle things, right? Too much noise, cameras at the wrong angle. Well, it's virtually endless. And if you've dealt with data, you've dealt with bad data, right? Because 90% of data scientists' time are trying to get the data into a form where you can actually do the analysis on it. And that's a huge problem for AI. So I think, AIs that can fix bad data, even if it's just to give it to other AIs, there's just an enormous amount of work to do there. I'm coming up against that competing with free alcohol thing, I think, pretty soon here.
Yes. And food. So I'd like to thank you for your amazing presentation, as Namita had already said. So thank you so much.
Thanks.
Ari, you're popular. So